In this talk, I'll be describing how we can make existing 3D pose estimation tasks geometry aware by taking into account perspective distortions in input data. In this problem setting, we want to leverage visual data either through images or 2D T-points to estimate the 3D pose of the subject. The 3D pose is a collection of 3D joint positions measured relative to the hip, which is a common practice in 3D pose estimation literature. Convolutional neural networks, CNNs, build upon translational invariance, and current state-of-the-art 3D pose estimators have seen great success using CNNs to learn from image data directly. Some use a separate detection stage and spatial transformer network, STN, to add scale invariance. Another popular approach has been using multilayer perceptrons, MLPs, to lift 2D to 3D key points. For this approach is generalized, though, the predicted or ground truth 2D poses are first centered. The commonality between all three of these approaches are that they all operate locally on the image. Each approach has a portion that removes global context with a form of cropping a local area of interest. However, removing global context comes with downsides. From the video, you can see that the cropped image of the skier is rotated and distorted when they are near the edges of the frame. This is due to the perspective effects that come from the image capturing process and depend on the camera's focal length. To address this issue, we propose perspective crop layers, or PCLs. Given an input image, the bounding box parameters for the region of interest, and the camera intrinsic matrix, PCLs produce a perspective-corrected crop of the image. Here we see a comparison between the perspective-corrected crop outlined in blue and the rectangular crop outlined in red. Unlike the rectangular crop, the skier is neither rotated nor distorted in the PCL crops. Another aspect that is lost when taking a rectangular crop is that the global pose no longer matches the cropped image. If we take a look at the rectangular crop and the global pose, you notice that they are misaligned at the edges of the frame. PCL accounts for this with a change of view direction. To perform this perspective change, we first define PCL's virtual camera at the same location as the real camera with its direction pointed at the subject. PCLs perform perspective transform between the real and virtual camera planes, a homography transformation that depends on the amount of rotation between the two. Lastly, since PCL is fully differentiable, it can be integrated into existing approaches as a pre-processing or integrated into end-to-end training. Here we can see that PCL inverse operation is needed, which transforms the prediction in virtual coordinates to global coordinates. It is simple as it's the 3D rotation from virtual to real camera. Here we show some results of integrating PCL into models trained and tested on the popular human 3.6M dataset. This histogram shows the improvement of PCL on the baseline with respect to where the 2D coordinates of the person's hip is in the original image. Blue regions represent areas where the baseline model with PCL outperformed the baseline with root centering. The most interesting result here is that we see that, with the exception of one tile, PCL consistently outperforms the baseline when the subject is farther from the center, which is where we see more perspective distortions. In absolute numbers, PCL improves the baseline by up to 15 millimeters in mean per joint position error, or MPJPE, which is a significant 27% decrease in error. Visually, we can see here that as we vary the crop between PCL and the rectangular crop, we see a drastic difference in the rotation of the predicted pose, with the largest differences highlighted in green. These results are generated using the exact same network with PCL, but we manually change the focal length between the intended ground truth focal length and infinity, which represents rectangular cropping. The improvements we see in the previous qualitative results are reflective of the overall improvement across all datasets, input modalities, and models that we test. It holds for 2D ground truth as input, noisy 2D detections, and for CNNs operating on images, and is consistent across all datasets. Along with directly comparing the performance of PCLs against baselines, we also analyze the efficiency that comes from using PCLs. The improvement brought about by PCL is as much as doubling the neural network parameters from 20,000 to 40,000. Determining the rotation angle to the virtual camera requires knowing the camera intrinsics. However, we've shown this ablation study that PCLs and the models trained using them are fairly robust to reasonable estimates of the focal length, roughly between 0.75 and 2 times the ground truth focal length. For more information about our project, please see our paper. We've also made the code for PCL publicly available and is compatible with PyTorch. Thank you so much for listening.